Okay, I'm back, and so here is what we've learned so far. You should now know what the frequency of an oscillator is, and it's given by the letter nu, and then the official metric units is the hertz. You should now know what the period of an oscillator is, and its abbreviation is going to be a tau, which kind of looks like a T, and then its official metric unit is the second. You should now know what the amplitude of an oscillator is. And now we've introduced these two equations over here. The frequency, the definition of what frequency is it's the number of times that something oscillates per second. And then we also now know what the definition of the period is it's 1 divided by the frequency. So ultimately, we want to try to figure out what is the frequency of a spring, so that when we put a weight on the end of a spring and then we pull it down and then we let it go, it's going to oscillate up and down. And what we'd like to be able to do is calculate the frequency at which it's going to be oscillating. So in order to do this, we need to know something about springs. Now, this information is coming from a future lesson that I'm going to do on properties of materials. And so I'll go into much more detail on that lesson on where do these formulas come from. But for right now, as long as you just remember that there are formulas for this and not to really worry about where the formulas are coming from. So here's the idea, that you're going to have a spring, and then this spring had a initial length. Okay, so this spring is this long right here. Okay, then what we're going to do is we're going to put a weight on the end of that spring, and it's going to stretch it out. So here's our weight, and this is going to have a mass m suspended from it. And then notice that it's going to stretch it out a little bit, so that the distance from here to here is going to be delta L. So L was this one over here. So this is the original length of the spring. And then when you stretch it out to here, that will be the new length. So we could, I don't know, if we want to call this distance from here to here, if you want to call it L sub nu, okay, then the change in the length would be take this number and subtract that number, and then that's going to be the change in the length of the spring. Well, in order to do this, it's going to take a force. Now, the force that is stretching the spring is going to be the force of gravity. So we're going to say force of gravity. Now, you might, so the formula for the force of gravity when you are close to the Earth's surface is going to be m and then g. Okay, so g, you can think of g as standing for gravity, but it's going to be called the acceleration due to gravity. And it depends on how strong the gravity is. So if you are on Jupiter, Jupiter would have more gravity, and so this number here would be bigger. And so we're going to find out that for Earth, it has a particular number, and I'll show you that number on the next slide here. So for the moment, the force of gravity that's pulling down this mass, force of gravity is going to be equal to mg. Now, this mass is not going all the way down to the ground, so there must be another force acting on it. So the force of gravity is pulling down. So if this mass is suspended, there must be a force that is pulling up on it, and I should draw it so that this arrow here is the same length as this arrow here. So they're equal and opposite, the two forces. So the force that's trying to pull this thing up is going to be called the spring force. And so this is going to be given by force sub spring. Okay, and it's going to be equal to a constant that depends on what the spring is made of. So are we talking about a rubber band, or are we talking about a shock absorber from a car? So depending on what the thing is, the spring is, it's going to have a different spring constant. And the spring constant is going to be telling us how stiff the spring is. So a rubber band would have a very small spring constant, and a shock absorber would have a very large spring constant. So this is something that's going to be given to you on the exam. I will tell you what the spring constant is for that particular system. So it's going to depend on the spring constant, and then it's also going to depend on how far do you stretch it. So it's going to be delta L. So that the further you pull the spring down, the more force there's going to be that's going to try to pull it back up again. Similarly, you could have a spring and you could try to push it together, and then that spring force would be trying to push your hands apart. So notice that the force is always opposite to the direction that you're either stretching the spring. So if you're pulling it out, then the force is trying to pull it back in. If you're trying to push a spring in, then the spring force is trying to push it back out. So this is going to be called the spring force. And so we can indicate this opposite effect by putting in a negative sign here. So putting in a negative sign in front of the C, so that's why that's there. It just tells you that the direction of the force is always going to be opposite to what you're trying to do to the spring. Okay, so what's the point of talking about all of this? Is I would like to be able to calculate what the spring constant is if I do some measurements. All right, so we got a spring. It has an original length of 10 centimeters. So this is the original length of the spring. It was 10 centimeters long. And then you're going to take a 30-gram mass and you're going to hang it from it, and then the spring now stretches to 25 centimeters. So now the new length is going to be 25 centimeters. What is the spring constant of the spring? So the first step is you're always going to write down what you're given and what you're looking for. So the initial length of the spring is 10 centimeters, but that's the wrong unit. We always want to use official metric units. So it's going to be 0.10 meters. The final length of the spring is going to be 25 centimeters, so that's going to be 0.25 meters. You always, always, always have to put official metric units into any formula. So we have to convert it to meters. All right, now the change in the length of the spring, we're going to subtract them. So 0.25 minus 0.10 is 0.15 meters. And now we've got this. So that's the change in the length of the spring. Okay, now the mass, M, is going to be 30 grams, but that's the wrong unit. The official metric unit for mass is the kilogram. And there are, 1 gram is like a paper clip. And a kilogram is 1,000 paper clips. So there are 1,000 grams in 1 kilogram. So we're going to need to take 30 and divide by 1,000. And that's going to be 0.030 kilograms. And then what are we looking for? We're looking for the spring constant. So we're looking for the value of C. All right, so how are we going to do this now? So now that we've got all of our variables there, we're now going to use this to calculate what the spring constant is. So the force that is pulling down on the spring is its weight, and this is going to be caused by the force of gravity. So the force of gravity is the mass m multiplied by g, which is the acceleration due to gravity, and is equal to 9.8. So little g, the acceleration due to gravity, is equal to 9.8 meters per second squared. We'll talk more about that later when we talk about falling objects and we talk about gravity. So just, it's a constant for Earth. And so every planet is going to have its own acceleration due to gravity. And then the force of gravity is going to be m multiplied by g. Now, that's what's pulling it down, but we said that what's pulling it up is going to be the spring force, this thing right here. That's pulling it up. Now, if this object is suspended, it's not shooting up into the air, and it's not falling down, then that means that these two forces have to equal each other. So the force of gravity pulling down is going to be equal to the spring force pulling up. So now what we can do is the force that's pulling down is negative mg. Negative because it's pulling down. But that's equal to negative the spring constant times the change in L, which is going up. And so the two negative signs, they cancel out. And so all we've got to do is plug in our mass, plug in the acceleration due to gravity, the 9.8 thing. We don't know what the c is, but we do know that the change in length of the spring was 0.15 meters. And then solve it for c, and now we've got the spring constant of the spring. Now, the good news is you're not going to do this on the laboratory or on the lecture exam. I am going to give you the value of c. You won't have to do this fancy calculation. However, in lab, we are going to do it. So in lab, you're going to have a spring, you're going to have a mass, you're going to have a ruler. And so you're going to measure this, you're going to measure this, you're going to measure the mass of the mass, you're going to do this calculation, and you're going to calculate the spring constant of the spring. So I just wanted to give this to you ahead of time so that you'll know how to do it in lab. All right, let's take a break, and now we're going to relate the spring constant to the frequency of a spring, and we'll do that in just a moment.